So welcome to the second session of today's webinar, which is operations and maintenance in respect of the new changes to IEC 61511. And just a little bit about exida in case some of you might not be familiar with exida. We've been in business nearly 20 years, and we provide a comprehensive set of services for functional safety, alarm management, cybersecurity, all the life cycle services associated with that. Plus, we also provide certification for products, both on functional safety, cybersecurity, as well as personnel. And some of you I see have already been on our courses or been on some of my courses. So nice to see you, and thanks for joining us again. We've developed a global network, and in fact we've just recently opened an office in India, in Mumbai, so you'll see that pop up now on the map, and as well as having other offices in Europe and Asia. In terms of our success, we actually have, according to ARC, 65% of the worldwide market share in device certification. We've also got over 100 experts now globally. We've done over 1,000 certification and assessment projects, and we've modeled over 500,000 SIFs now using Excellencia. Again, quite a few of you will be very familiar with the reference materials we provide. We've written quite a number of books, and we have the SERH, which is the Safe Equipment Reliability Handbook that has all failure rate data that goes into the Excellencia tool. We also provide quite a bit of free information. You know, we do these webinars regularly, but we also have white papers, and we do publish a lot of material. We have the SAEL, the Safe Automation Equipment List, where you can find certified devices, and we also have the SILstat data website where you can compare failure rates for final elements, and also we now have the site safety index where end users could see how they measure up to the site safety index in terms of the maintenance capability. Those of you who are familiar with me know that I've been around for a while now, been in industry for 40+ years, started off working for an avionics company doing hardware software development, then moved into the safety world, designed ESD and fire and gas systems and components, as well as fire detection. Did that for about 16 years, managing development, and then moving into the automation world rather, with a DCS company for another 15 years, and finally coming back into safety about 6 years ago. So I do a lot of the functional safety training for exida, and again, as I've said, I see a lot of you have already been on the courses and know me. I've written a number of publications and co-authored papers, etc. So by way of introduction, the IEC 61511 has been around now since 2003, and prior to that, the IEC 61508, which is known as the umbrella safety standard, the first draft was published in '98 and the first edition was in 2000. And that was really targeted at manufacturers of devices that would be used in safety applications. That then spawned some other standards known as sector standards. And 1511 is the process industry sector standard. Both of 08 and 11 are based around a safety life cycle, and both are performance-based standards. Whereas in the past, prior to 1508, we had the DIN BDE 0801, which was prescriptive. In other words, it said, this is what you have to do, and this is how you do it. Whereas with a performance-based standard, it says, this is what you need to do, but you also need to measure your performance. And how you do that, how you implement it, is entirely up to you. But again, it's a performance-based standard, so you are expected to have key process indicators or key performance indicators to be able to measure it. In general, 1511 has been widely adopted in most industries, petrochemical, chemical, and hazardous processes. And to a certain degree, the first two stages of the life cycle, which is the analysis stage or analysis phase and the design and implementation phase, are pretty well followed. The final phase, which is operational maintenance, is one of the phases which has not been so well followed. And this is what we're going to talk about today and what's changed in 1511. 1511 has been beefed up to be more rigorous with its requirements specifically around operation and maintenance. And the other thing I tell my class is not to forget that the 1511 standard is written by end users for end users. So the majority of people involved in the 61511 Standards Committee are from end user companies. So it's not written by academics. And they've recognized that there is still significant need to be following the operation and maintenance much more carefully and closely. Because again, the whole point of the safety life cycle is to help us manage risk and balance what we can tolerate in terms of target risk with performance, what we actually achieve. And if you do it right, if you actually follow the safety life cycle, it will save money. Because again, if you are doing your hazard analysis correctly, if you design your SIFs to go in your SIFs correctly so that you have the right target integrity levels, and you're doing all the maintenance and the proof testing, then you will help reduce the number of potentially spurious or unwanted trips. And we all know that when you have a trip, not only is it not desirable, but it's also hazardous, because once you've tripped, you've got to start up again. And most accidents have occurred either during startup or during maintenance. So obviously, we don't want to do that. On top of that, if we do have a trip, it can be significantly costly, because depending upon the process and the application, it may take a couple of days to get fully back up and running. And that will have a significant impact on production and, of course, on the bottom line. The other thing about the safety life cycle is not to be cherry-picked. You can't choose to do some of it and ignore doing others. So you have to follow it in sequence. And if you do it right, like I've said, the benefits will certainly come back in terms of improved profitability through much less downtime. So where are we? We're down here in this section of the life cycle, the operation, the maintenance. And if we look at it in more detail, we see that operation and maintenance is really just one box. Another thing I say on the courses that I teach is that if you're old enough to remember the old adage of 20-20-20, where we used to say 20 weeks in design, 20 months in implementation, and 20 years in operation, then we're going to be spending 95% or more of our time in the operation and maintenance phase, which is where, if we don't do things right, we could negate all the good work we did in the previous two phases. Because if our SIS and its SIFs are not properly maintained, they will degrade, and they will degrade fairly quickly, especially if you do not replace devices at the end of the useful life, because then you won't have any SIL at all in your SIFs. So let's take a little closer look at this. Some specific O&M items that have been called out now. The maintenance plan is required, and we need to have specific response plans for given faults. Now here again, it's before we start operation, before we do our startup, we should make sure that all the maintenance procedures are in place. All the proof test procedures have been written. And in fact, I always encourage people and say that during the pre-startup safety check, it will actually benefit you if you run through all the proof tests, because you get what I call a twofer. The first thing you get is that the maintenance people will have confidence that they can actually follow the proof test and they can run the proof test. Secondly, when doing that, they might actually find potentially dangerous faults. Now remember, the purpose of proof testing is not to prove that the SIF works. The purpose of proof testing is to try and find dangerous faults that the automatic diagnostics have not been able to find. So it's important to make sure that the maintenance people are comfortable. And I always tell designers on my courses that don't design in isolation. You need to make sure, as a SIS designer, you need to talk to operation and maintenance people to find out what sort of sore thumbs they get. Because when designing a proof test, you could design a really excellent proof test with high coverage, but if it takes 7 hours to do, well, guess what? It's not going to get done, or at least not get done the way you want it to get done. So it's important to make sure there's buy-in from the maintenance people on it and that they can realistically run these proof tests. The other thing that's now called out is that we have to do adequate validation after replacement of any device. Now, what does that mean? Well, what it means now is if you have to replace a device in a SIF, you need to rerun the proof test. And again, if you make any application program changes, the SIFs that are affected by that application program change will also require to have the proof test rerun. Now it's also saying that diagnostics must be tested, because again, if you're relying on a certain level of automatic diagnostics, then they have to run. So now we have to make sure we can test the diagnostics, especially if we're feeding diagnostic alarms or diagnostic alerts to maintenance people in the maintenance cabin. Now we also need to collect data related to demand rate and SIS reliability. The standard says now we have to, and I love this word, periodically. We have to periodically do a performance assessment. So it doesn't say what periodically means in terms of time frame, but basically what that says now is that we have to perform a functional safety assessment number 4, which is a periodic performance assessment where we need to look at all the data we've gathered in terms of demands, near misses, because again, if we've had any valves, safety valves go off, or relief valves go off, that means that there's something not right. So these need to be looked at as well. Bypass is another thing that's now specifically defined in the standard. So again, bypassing, as we all know, is the mechanism by which we can take a SIF out of service. Now, when a SIF is taken out of service, of course, what happens to the PFD average for the SIF? Well, of course, it goes to 1 because the SIF is no longer available to perform its function. So it's important now that this is understood, and if a physical bypass is put in around the final element, now we have to also consider other means of mitigating, because if the SIF's out of commission and we get a demand, how are we going to, number 1, see that demand, and number 2, how are we going to respond to it? So it's important, and the operators and the maintenance people need to understand, again, what each SIF is protecting against, the hazard it's protecting against. What are the overrides, bypasses? What are the startup conditions? If there are interlocks, what are those? If there are permissives, what are those? What happens during normal and abnormal operation? What happens if we get a fault? All of these things. So the standard calls this out now and requires a compensating measure to be specifically defined. So as I said, if we have a SIF in bypass, that means the SIS is now partly disabled or degraded, depending on how many SIFs we have in bypass, whilst they're either being maintained or repaired. So we need to have other contingencies, other means of being able to mitigate if we get a demand. And that may mean having a maintenance guy go out into the field and keep an eye on some gauges. It might mean the operator in the control room monitoring a particular part of the process area and the screen more closely. Whatever it is, it has to be defined, and this is now called out in clause 3.27 and 16.23. To that end, when it comes to bypassing, now we have to define a maximum permitted repair time. Now remember, in the SRS, we have to define our mean time to restore. So, for example, if we've said in the SRS that everything is 24 hours except final elements, which are 72 hours, that means that from detecting a problem to bypassing or taking it offline, diagnosing what the problem is, fixing the problem, and restoring the SIF to normal operation, that's the MTTR. So if we've said 72 hours for final elements, we need to determine what would be the maximum repair time. So let's say if we did say 72 hours, but this occurred on a Friday night and we found that the failure was such that we didn't have the necessary spare parts to repair it on site, that would require going back to the vendor or having something specifically machined in order to be able to fix and bring the final element back online. That may take longer than the 72 hours. So we might say that the maximum permitted repair time is, for example, 100 hours. That needs to be defined and that needs to be included in the SRS because it needs to be monitored. So it's one of the KPIs that we should be measuring. Now again, standard doesn't say what that MPRT has to be. It just says you have to specifically define it, or it has to be defined. The reason it's in there is because, again, some end users were leaving SIFs in bypass for significant periods of time because the maintenance people didn't quite have the time to get around and fix what needs to be fixed. So they just put it in bypass and left it. So you can no longer do that without some form of mitigating requirements. Here again, what it says is when we do put something into bypass, the operators obviously have to be involved because they have to know it's in bypass. So they need to be informed of the procedures that are applied before and during bypass and what needs to be done once the bypass is removed, because we might have to reset a few things or it might take time to settle down, which will cause some potential process upsets initially. And then what is the maximum time allowed for the bypass? This needs to be reviewed regularly. And then it says that you can only continue in bypass if hazard analysis has determined that the compensating measures provide adequate risk reduction. So remember, the SIF has a target SIL. That SIL is an indication of how much risk reduction that SIF is providing automatically. If we then take it offline, we have to have other mitigating measures that enable us to achieve at least the same level. Now for SIL 1, it's probably not that much of a problem to be able to do that, but once you get into the SIL 3 realm, that's a much more difficult task. Also, we now have to have bypass logs. So if we do put SIFs in bypass, we have to document that, and of course it has to be authorized. It has to be authorized by somebody who is senior, competent, and responsible. So this is another area where the standard has been beefed up again, the requirements for competency and the requirements to clearly define roles and responsibilities. 1511 now calls out for a properly and well-defined O&M plan, which will include SIS maintenance. So in other words, mechanical integrity. So we need to have all our tests and test procedures in place to verify operation of the safety instrumented functions. So this is where we have our proof tests. Now here again, in the SRS, we would have defined a proof test interval and we would have defined a certain level of proof test coverage. This is then used when we do the SIL verification calculation. So it's important that we monitor the frequency of the proof testing when we're in operating mode, so that if we're missing our proof testing intervals, then by how much are we missing the intervals and why are we missing them? So again, if you have an 18-month or a 2-year proof test interval and you miss it by a week or two, it's not a big deal as far as the integrity goes. However, you should be looking at why is that. But if you have, say, an 18-month or 2-year period and you're missing it by 3 or 4 months, now that is a big deal and will have an impact on the SIL for the SIF. So that needs to be clearly understood, and the operations and maintenance people need to have the training to be able to understand that if they're missing it, then they've got to look at reasons why. What is the operational response to faults and failures? So if we do a proof test and we find a potential problem, now what? Because we've started the clock on the mean time to restore. So we need to have procedures in place, and the operations people need to understand what they need to do when a fault is discovered. So here again, one of the key performance indicators should be how frequently are we doing our proof testing, and does it match up to the SRS? These are what should be built into what's known as leading indicators. So again, leading indicators will give us an indication that we may be saving things up for a future event. We're not completing our maintenance as required. We're not doing the calibration regularly. We're not doing the proof testing regularly. We're not doing proper training of our maintenance people. All these issues could build into a future event down the road. And so these are leading indicators to help us head those off and maintain the target risk reduction that we're looking for from the system. Conversely, the lagging indicators are a set of indicators based upon events that have happened. So for example, near misses, any trips, whether real or otherwise, faults, failures, all of those things should be logged and should be reviewed. This is part of the periodic review. Now again, in the SRS, we also have to define a target spurious trip rate. The standard says we need to define it. It doesn't, again, give you any minimum requirements. So for example, if we said our spurious trip rate target was no more frequent than once every 15 years, and we've had 3 trips within the first 6 months, we need to look at why we've had 3 trips in the first 6 months. So this is, again, part of the lagging indicators. One of the things that I talk about in my class is checklists, and I'm a great proponent of checklists. The example I use all the time is the air pilot analogy. Even though pilots may have flown thousands of hours, every time they get into the cockpit of an airliner, they go through their checklist. They don't rely on their memory. They follow their checklist. So one of the things that we could look at doing is developing a safety checklist, because our O&M plan should be a working document designed to make sure that each SIF of the SIS is maintained to meet its designed integrity. And so we obviously need our procedures to be in place, especially when it comes to providing updates or modifications to the SIS and its SIFs. Another expression I use in my training classes is RTFM. And those of you who have been on my class will know what that means. It means read the flaming manual, because we have to make sure that the manufacturer's safety manual is followed, especially when it comes to replacing equipment, to make sure that it's properly configured. If it needs any programming, it's properly programmed. It's properly configured, if that's links, etc., for the application it's been designed to be used in, and also to meet the requirement for the SIL. And this needs to be done because part of our mechanical integrity should be to identify and monitor useful life. Now, useful life is not the same as mission time. Some people get confused with that. It's also not the same as the mean time to fail. So if a manufacturer in his safety manual is saying this device has a 5-year useful life provided you follow this proof test regime, then if it hasn't failed at the end of the 5 years, we should be looking to replace it. I did a webinar a little while back on if you're using run to fail for your SIS, think again. The reason is that all of the reliability calculations, the predictive analysis we use with the PFD average calculation, is all predicated on a simple fact, and that is constant failure rate during useful life, where we can say that the relationship between the mean time to fail and failure rate is mean time to fail is 1 over lambda, the failure rate. And that is because we assume this average over the useful life. In other words, we take an average of the flat portion of the bathtub curve. So this is constant failure rate. Once we get outside of constant failure rate, we're into wear out, and wear out is totally unpredictable. And therefore, the notion of constant failure rate doesn't work, and therefore our PFD calculations and our SILs don't count for anything. So this is why it's important as part of mechanical integrity to know from the safety manuals, the manufacturer's safety manuals, what the useful life is, and then have a program in place to start replacing equipment as the useful life comes to an end. And in a SIF, you know, your sensors, your logic solver, and your final elements, actuators, valves, are all going to have a different useful lives. Establishing the leading and lagging indicators will definitely help you with your performance analysis, and again can act as a checklist to help us look at, you know, okay, we're missing our proof tests. Why are we missing our proof tests? Let's go back and have a look. So all of that is designed to help us. We now have to have O&M procedures that cover things like routine methods required to maintain the as designed, in other words, the integrity of the SIS and its SIFs. To ensure the consistency of proof testing, as I've said before, we need to make sure that if we're keeping as far as possible to the requirements in the SRS. What information we need to keep on system failures and demand rates, what information needs to be maintained from audits and tests, and of course, how we collect data on the demand rate and the reliability. These procedures need to be followed, and of course, when we have failures, then we need to have procedures for doing the diagnostics and repair. Then how do we validate? Remembering, of course, now that if we have to repair or replace any piece of equipment in a SIF, we have to rerun the proof test to make sure that the SIL hasn't been compromised. We need to have maintenance reporting requirements, and we'll obviously have to track our performance. The skills I've mentioned already, we have to make sure our O&M personnel are competent. So they need to understand how the SIS functions, what happens during bypassing, normal operation, startups, resets, manual intervention, and what happens when we have diagnostic alarms. We also need to make sure that there's a regular assessment. Now here again, the standard says periodically assess, doesn't tell you what that means in terms of how you do that and when you do that, but you would need to have some program in place whereby you might do it twice a year, where you'll review or do an assessment of your O&M personnel, and how you do that's up to you. That may be a form of some practical plus maybe some written requirements, because the purpose of the proof testing, as I've said already, is to reveal potentially dangerous faults that could cause a failure on demand. That's what we're trying to avoid. Especially when we come to putting in new components, because sometimes, of course, manufacturers are going to turn around and say, well, you know what, we're discontinuing this particular model because we have this new model now that can do everything the old model did, plus has a few more bells and whistles. Well, that's fine. But again, if you're going to be putting that in the system, somebody has to do, who is competent, senior, and responsible, has to do the proper assessment. And then if necessary, if training or further training is required for the O&M people, then that needs to be done. We also need to keep training records. So if we're doing assessments, then those need to be documented so that they can be brought out during any audits to make sure that we're covering things. So what happens in practice? Well, a lot of this falls on end users, which is, in some cases good, other cases not good. It really comes down to the safety culture of the company and the management team. It's very difficult if the safety culture is not there and management is pushing back on every single dollar that's spent regarding any preventative maintenance, any training, ongoing safety lifecycle work that's essential to be done. Because it's like pushing on a rope. You're not going to get very far. Also, the end users have to ensure that there are adequate procedures as well as an adequate documentation and tracking system to be able to show. From an audit point of view, we need to record spurious trips, process demands, failure events, etc. All of that has to be recorded. And of course, it falls heavily on the O&M personnel to be diligent in recording the required information. Now, I know that with some installations where maintenance people have been cut back, it's been very difficult for the maintenance guys to keep on top of this, especially if they're still using paper-based systems, because even though they may be doing the testing and recording it on paper, there's usually some requirement to upload that into some form of SAP, asset management system, enterprise management system, whatever. And that requires more work to be done. And I had one customer that confessed that, yes, we do that, but we don't have time and we get to it when we get to it. So, of course, that's also another potential problem because paper can get lost. The proof testing requirement is well defined in there in terms of potential to reveal dangerous failures and the regularity of the proof testing. Also, here again, when I teach the class, this is one thing I stress. The proof test should not just be an electromechanical test. It should be a visual inspection, because what you should be looking for is signs of corrosion, loose wires, unauthorized modifications, things that should not be there that could potentially cause us a problem. The proof test intervals, as I've already said, should be carried out in accordance with the requirements of the SRS and the mean time to restore. Our MPRT now has to be observed for bypassing the SIF. So as I've said, if we've said 72 hours for final elements and we've set our MPRT at 100 hours, then we need to make sure that we're not exceeding that. Or if we are exceeding it, then the investigation to root cause needs to be done again by somebody who's responsible, competent, and senior, and the personnel regularly assessed. All of this, of course, falls into management of change realm when we're looking at maintenance of the SIFs in terms of replacement at the end of useful life, any changes due to obsolescence, any other changes. And changes can come in the form of, if our performance is showing that our overall safety performance is below the intended design target, we may end up having to make changes. If we're finding we're getting a great deal of systematic faults that are resulting in spurious trips, then we need to look at that. If our incident or accident experience is actually worse than we had predicted, we also need to look at that. But on the other hand, it might be that operation or production is requesting changes because they want to put in another process line, and that may require some additional SIFs to go in or additional hazard assessments to be done. There might be new or amended legislation, as in the case of the change to IEC61511 in 2016. There may be modifications to the equipment under control itself or modifications to the safety requirement. In that case, we have to do an impact analysis study. And this needs to be done again by somebody who's responsible, senior, and competent, because it may have an impact on the hazard and risk analysis and may require going back to the analysis phase of the life cycle. So all of that has to be assessed and done carefully, because you need to understand what's the potential impact to the SIFs and the SIS. So how is the data recorded? Well, the standard says thou shalt maintain records that certify proof tests and inspections were completed. Again, it doesn't tell you how to do that. And of course, we know that proof testing is designed not to prove that something works, but to find potentially dangerous faults that could cause us to have a failure on demand. It does say that the records need to include a description of the tests and inspections, who did it and when, any serial numbers of the equipment, and what were the results of the test, including the as-found condition, because that's very important. If there is a failure, you need to know what the as-found condition was, as well as the actual test that was performed. Even though 61511 doesn't define how these results are recorded, 1508 does recommend some data collection standards that could be followed. The ISO 14224, which is 2006 edition, the IEC 61511-3, 2004, and NMOR, which is European, NE93. Right now, a lot of plants are merely recording either using paper or some sort of Excel-based tool. Clearly, this is an area where technology can help. So if you have a software tool that's on a handheld or tablet, this can clearly save time and money. And the tools should be able to record functional safety statistics, including performance metrics, life events, etc., which would be demands, either real or spurious, inspection and proof testing, maintenance activities, and failures, as well as any discrepancies between expected and actual behavior. Demands on the SIFs and its SIFs are very important. So we need to be able to determine, if we've had a demand, whether it was due to a layer of protection failing, and if so, which layer of protection failed. It then enables us to look at the demand frequency to see if the demand frequency we predicted from our analysis phase is the same, or whether we're experiencing higher demands than we thought that we're targeted for. And of course, any discrepancies between the expected and actual behavior need to be analyzed and any modifications implemented. So SILstat is a tool that can help with this. And again, if you use Excellentia right now, you can export the Excellentia design, which has all the equipment, manufacturer's equipment, model numbers, etc., as well as all the proof tests. And you can do it on a hierarchical basis. So you can look at it geographically if you have plants around the world. You can drill down, and in this example, you can see at the top left here, we're looking at the United States of America, we're looking in Pennsylvania, and we have an installation at Penn State University, and it happens to be a batch chemical reactor, and the hazardous scenarios we're looking at is high pressure alarm, high pressure alarm, and there's a SIF in there, and a PSE. And you can see from the diagram below that we've had a failure due to the high pressure alarm and the high alarm, but the SIF worked. So we avoided any potential hazardous outcome. And again, when we're doing proof testing, when we're running a proof test, here you can see we're looking at a HART communicating transmitter, and we see that when we were trying to go to 3.7 milliamps, it failed because we could only get to 3.5 milliamps. And that's outside of the tolerance level that's defined. So again, you can have event device failure recording. So any devices that fail would be an event log, and you could call up the event log. And if you've then, in this case, we haven't performed any corrective action and we haven't classified what the failure is because we haven't looked at it. But once we've looked at it, we could update with cause and with corrective action. And here again, if you look at the live event recording capability, this shows you using colors where we had failures. So you can very quickly spot devices that failed. Then you can compare your actual performance with your assumed performance. So again, if the risk reduction is adequate, we would continue collecting data. If it wasn't adequate and we were getting a higher than expected hazard risk, then we would need to go back to the analysis phase to reconsider. And again, if we've got higher risk reduction than we actually need, then that means that we've got a slight over-design situation. And this is the beauty of a performance-based standard. If you've collected data and you've accurately recorded it, and you can see that your performance is actually better than you originally designed for, then that can help you with reducing maintenance costs, because you might be able to stretch out the proof test intervals, and which means you're doing less frequent proof testing, and that can save on the maintenance costs. But it's important that the data is collected properly and analyzed correctly. Benefits of having an automated recording system, of course, is that it will enable us to do this detailed analysis of failures, because we can look at specific addresses, tag numbers, for example, the device type. We can look at how we can reduce false trips. Like I said, if we've been getting a higher number of false trips than we had planned for, we would look at that down and analyze it down to root cause. It could be some systematic problem somewhere along the line. It could be that we're using the wrong device, or the device isn't rated for the environment or the application. In other words, if we have a severe service application and we've not used a device that's suited for it, it might fail more often than it should, resulting in a spurious trip. We can then compare this actual versus expected performance, so we can then make sure that our risk reduction is adequate. And if it's not, we can identify this and then go and take the corrective steps to address that. We can also create and track leading and lagging indicators to help us manage risk. If we find that we've got more risk reduction than adequate, like I said, that allows us, it gives us options. We can look at either maybe redesigning, if redesigning is appropriate, or extending out the proof test. The point being, it gives us data that we can use when we come back and do the 5-year PHA review. So we can go back and use that real data that we've got from the field. I've mentioned already the ability to reevaluate the frequency of the proof tests. The other thing is it can help with communication between plant and departments, because it's using consistent data. Now, another thing that I say when I teach the class is I tell my students, you have to remember the 4 R's, and that is that it has to be the right data at the right place, in the right format, and the right time. Because most of the time, problems occur, so systematic problems occur between the interfaces when information is being passed from one group to another group. So if you're all using consistent data and a consistent database, the chances of that happening is reduced. Okay, so let's summarize. The point being with the safety life cycle is that we're looking to manage risk. We don't want to ignore it, and therefore operation and maintenance is a crucial part of the safety life cycle phase and needs to be given the appropriate attention. To have an appropriate safety first culture. This is something that is a problem in organizations that don't have it, because when it comes to training and making sure our people are competent and understand what needs to be done, this is where things fall down. We need to have proper operating and maintenance procedures in place. These need to be followed. There have been several accidents, BP Texas City being one of them, where the operators violated the startup procedures. If the procedures are not followed properly, you will have potential problems. And that, again, would be a leading indicator if procedures are not being followed. Develop a safety checklist, which helps with consistency and means we don't miss anything, and develop and maintain leading and lagging indicators, because if used properly, that can also help us improve our risk management. Undertake regular employee competency assessments. Again, how you do that, entirely up to you, but make sure the proof testing is in line with SRS requirements. Remembering, of course, the SRS is not a once and done document. It shouldn't be sitting on some manager's shelf. It's a live document. It needs to be maintained and updated, and it needs to be where the action is. So it needs to be with the maintenance people as well. Record all your maintenance activities accurately and faithfully. Make sure if you're using software tools that they're suitable for the task, and you can also use them to help analyze failures, false trips, and the performance. The whole point being we keep our plant personnel and the plant safe by following these requirements. So just a little promotion here about the training. We've actually just developed this course, which is specifically aimed at the operations and maintenance requirements in the 2016 edition of 61511. So if this has piqued your interest and you'd be interested in doing that, please feel free to contact me or go through the website. If you want to know more, you can follow us on Twitter, Facebook, and LinkedIn. And of course, if you have further questions after this webinar, you can always contact me. So at this time, I'll open it up for questions. Let's see what we have. Somebody is asking me if I work for ICS Triplex. I worked for ICS in the very early 80s, which then became ICS PLC, and I was general manager of ICS Technology. Ultimately, it became ICS Triplex, which is now part of Rockwell, of course. And I did know Peter Hall very well. I also know Alan Renkum and Pete Skip. Okay, so we are end user of SIS systems, so can we use the collected data to make SIL assessment by ourselves? Well, the problem is, yes, you can, but you need to prove independence. So the standard says independent. Now, it doesn't necessarily mean you have to go to a third party, but it's easy for people to go to third parties because that shows clear independence. As long as you've got people who are not involved in the design, that are competent. Now, here's the requirement, and this is why it's in 1511 now. Competency is one of the major issues. Proving competency is important. So people have to be competent, they have to be responsible, and again, this has to be clearly shown. Any other questions? So I did have quite a few questions this morning concerning useful life. And some manufacturers overstate useful life. That needs to be looked at. And here again, we can help with that. There's another question regarding mission time and instrument replacement. Can we take credits of partial stroke test results and determine whether the control valve needs replacement or not when its mission time is approaching? Here again, RTFM, read the flaming manual. The manufacturer will say that if you do a partial valve stroke test, it will give you this much in terms of capability of finding dangerous faults. In some cases, it won't change the useful life. It's primarily to make sure that you maintain the device so it will last, or at least it will be able to achieve its useful life. Mission time, and again, people sometimes get confused with this. Yes, mission time is usually set by the end user, and normally what the end user will look at is with the SIF, the thing or where they have to spend most time is replacement of the final elements. So some end users will use the useful life as a guide and say, all right, if my valves are good for 10 years, assuming I do all the maintenance and the partial valve stroking, etc., then that will be my mission time. Because at the end of the 10 years, I want to shut down, I want to completely refurbish these things or replace them. Because again, in the SIF, let's say your sensors are good for 5 years, logic solver is good for 15 years, you know, your actuator might be good for 5 to 8 years, and your valve may be up to 8 to 10 years. So again, it's all a question of the end user practice, but also the environment. Because again, if you're under severe service or you have a tight shutoff requirement, you may end up having a much shorter life. What is the difference between MPTR and MTTR? As I mentioned, mean time to restore is the normal time from detecting a fault to analyzing what that fault is, to rectifying the fault and bringing the SIF back online. That is the mean time to restore. And usually end users will say normally 24 hours for sensors and logic solver, but the final elements could take longer, and they say 72. So you would set your maximum repair time to be maybe 100 hours or maybe 150 hours, whatever you determine that to be. Because if you're going to be putting, and this is for online being in bypass, if you're going to be putting the SIF in bypass, then of course the longer it's in bypass, the more stringent you have to be in terms of making sure you have adequate mitigation in place should a demand occur which requires that SIF to come into action. And because it's in bypass, it can't work. So again, that has to be considered carefully. Somebody's asking about a copy of the PowerPoint presentation. We do make this available at the end. Jitana will be sending it to people as a PDF. How do we evaluate human, I think that means reliability, performance in the SIF? Well, again, that's part of the assessment. If you're looking at competence, if you're looking at how well trained they are, you need to come up with tests. Now, some of the logic solver guys provide simulation tools. And I know in my previous company, we had a simulator that was based upon using the actual graphics and application program that was in the real system, but it was in an offline system. So you could have a senior guy go in there as an instructor and throw curve balls in to the process, cause upsets, and see how the operators respond to that. That's one way of doing it, or you might use a combination of testing or just reviewing with your most senior and competent people. So again, this is why the standard does not define what it is or how it is you do this. It leaves it up to you to do this. And of course, another way is to send them on courses where they can get a certificate or they can get some education units, all of which can be used to show ongoing competency development. Okay, on which part of the PFD, I assume that's average, calculation should we incorporate site safety index? Well, that's an interesting one because the site safety, let me get my teeth in straight. The site safety index is a concept that we came up with because in our experience, we were finding that for the same piece of equipment, the failure rates between sites could be as much as 2 or 4 times different, depending upon the maintenance capability of the site. So again, this comes down to culture, this comes down to competence training and following through on the maintenance plan. So we developed this site safety index, which is, it's basically 5 levels. You have SSI 0, which means that you're doing the bare minimum when it comes to maintenance, up to SSI 4, which means perfect maintenance. So you basically, you're doing everything on time, you're logging everything correctly, you're making sure all your repairs are done according to the SRS, you don't leave anything in bypass, everything's done correctly, your people are trained and properly assessed. Now, very few companies could actually achieve SSI 4, but the idea is to get to at least SSI 2, which is good, and SSI 3, which is near perfect. Because what we've found is that if you go from SSI 4 to SSI 0, you will drop a complete SIL level. Because again, if you're not doing this maintenance properly, if you're not doing the proof testing according to the time period in the SRS, you are going to degrade fairly quickly. So we created this, and if you go to the Site Safety Index, There are, I think, 40 questions, and if you answer them honestly, it'll give you a score that tells you, okay, you're at SSI 2. Now, in Excellencia, our Markov model, we take that into consideration, and we have an algorithm which we can apply that will degrade the SIL calculation depending upon if you're SSI 0 or SSI 1 compared to SSI 2, SSI 3, or SSI 4. Excellencia automatically defaults to SSI 2 for each of the sensors, the logic solver, and the final element groups. And you can change that. And if you have Excellencia, if you go in there and change it from good to 0, see what it does to the risk reduction factor in the PFD average. And you'll see it has a significant impact on it. There's another question. In the O&M, can we use the same method used during the design to verify the SIL of the SIF, or can it be possible to use the other one? Depends how you did it. If you've used simplified equations, then no, because simplified equations shouldn't be used. If you've used Excellencia, then again you can feed it back into Excellencia. Again, if you have SILstat, you can automatically do that. So it's consistent, and it'll just use the failure rate data that's been gathered. Any other questions? Okay, well, if there are no other questions, we're almost at our hour. I will thank you all for attending. I hope you found this informative and useful. There's my email address, so if you think of anything after the webinar, feel free to drop me a line. I'm always happy to hear from the people who attend the webinars, and I will answer these questions as best I can. Thanks again. And the slides will be sent to you.